Hello, I'm Schwa, and if you let me, I'd love to be your math teacher. So, I'm making a video series, sort of an introductory video series to the art of mathematics. I've been studying mathematics at university level for 3 years now, and I've been loving it. Math is a huge part of my life, and I've noticed that a lot of people don't really like math, and a lot of people don't even really know what math is, what it's all about, what's the essence of math. Why do people care? Why do people do math at all? And I would love to get into some of those questions, tackle those questions, and try to teach you all a little bit about why math is beautiful and why it's something that should be studied and encourage you and stuff like that. So I would like to dedicate this first video to talking a little bit about math in general, right? Like why I find it interesting, why maybe people should give math a second chance, stuff like that. And then we're going to move on to really think about what math is, what numbers are, how we can construct numbers or fundamental objects at play, and what else is there. Maybe there's going to be functions, maybe there's going to be some stuff that you might not even be that aware of, like relations. We're going to look at the basics, and I'm not going to assume a lot of, or maybe any mathematical background almost. Of course, it's helpful if you've encountered numbers like 1 or 2 and pi and stuff like that before. It's helpful if you've done simple addition, simple multiplication. So if you know that 3 times 5 is 15, then you're already doing great. So it helps a lot if you have, basic sort of math under your belt, like arithmetic. But if the thought of functions makes you scared, or if you've never heard of a derivative, that's okay. We're going to take this one step at a time. And of course, you might need some other supplementary material sometimes. So occasionally, of course, it would be wonderful if I could explain something and everything would make sense on the first try. But unfortunately, sometimes you might have to ask in the comments, or you might have to Google search what something means. Of course, I'll try my best to explain everything the best I can, but sometimes it's also good to not fear and try to look for some stuff on your own if there's something that's less familiar to you. But my hope is that even people who never struggled with math at school, even people who've maybe they're on their first year of university studying math, I'm hoping that many different kinds of people could benefit from these videos, because I'll be looking at these things, I'll be looking at math through a slightly maybe unorthodox view, because I will be trying to get to the nitty-gritty without making it super formal, super impossible to understand, super advanced, or anything like that. So I'll try to deliver what I think is beautiful, like the heart of the subject, without maybe every single little formal detail. I don't know how that's going to work. I don't know if that's going to work at all, but that's sort of my goal here. But first, of course, I would like to talk a little bit about what mathematics is. And it's a very difficult question. It's certainly a question that I have given different answers to at different points in my mathematical career. So for example, I remember when I was younger, I think I was like near the end of my high school. I thought about the question of what is math, right? How would I define math? And back then, so this is old me, the old me defined math as the study of change. And why did I say that? Well, for those of you who are familiar with calculus, if you're not, don't worry. But obviously in calculus, we study these derivatives, which is like the rate of change and stuff like that. So that might have motivated me to say that mathematics is all about the study of change. But change, it's a very abstract word because it sort of implies that there's different objects, and an object can turn into another object somehow. And that's a very common pattern in mathematics. So things sort of morph around, and you can interpret them, see them in different ways. Like, for example, this 3 times 5 here, maybe we can think of this as this 3 and this 5. When you put a little dot in between them, then suddenly this expression magically turns into 15. So that is kind of like change that's happening. This 3 and this 5 changes into 15, kind of, right? But change, it's a very loose word. It can mean a lot of things, so maybe it's not such a surprise that it also can occur in mathematics. But as I've grown older, right, I've maybe become less certain or less sure of what mathematics really is, or how I should describe it, because mathematics, it's a lot of things. It's a very wide subject. It's a very broad subject, right? There's a lot that can be classified as mathematics. So there's economics, right? We can think of supply and demand. So there's I don't remember how these graphs are drawn because I'm not an economics student, but maybe there's supply here. I don't know if you can see that, but there's supply on the x-axis, and maybe there's demand on the y-axis, and then as supply goes up, demand goes down, or maybe rather, as demand goes up. Actually, I just realized I don't know how economics works, but anyway, maybe you get the point. When people think of math, they often think of money, because money is often expressed with numbers, and numbers are certainly a very, central part of mathematics. So yeah, there's this real life applications. There's economics, right? But then there's more abstract fields of math. So, maybe you've seen equations before. You probably know, like maybe you've heard of the warning that sometimes people give to middle school or high school students, where it's like, oh, I enjoyed math in elementary school, but as soon as they put letters into it, oh, that's when it all got bad. So you might think of equations, right? Equations. So we might have 3x plus 2 equals 5. An equation like that. And here we have an unknown variable. And when we think really deeply about these unknown variables, and what we're really doing here, what these operations are in their general form, we get what's called abstract algebra, and that's very scary indeed. But there's this like abstract side of mathematics. Then there's this very concrete economics side of mathematics, but obviously they're intertwined, of course, as well, because if you're doing economics, you might have equations that you need to solve, etc., etc. Right, but what do I think is mathematics, right? I think mathematics, and I don't know if I can draw the human brain here, but let me just say one thing real quick. So we, as humans, so this is trying to be a human brain, right? So we as humans, we are not biologically designed to do math, in my opinion. On the other hand, I would say that we are biologically designed. Well, of course, the word designed is like, that's a little, sus. Like, what do you mean by that? But what I mean is, there was great evolutionary pressure for us to develop language, right? Those of us who were better communicators, did better out there in the wild. And, maybe it's a little sad, but it's also partly true even in today's society. Better communicators often get farther in life. Of course, communication is something, I think everything is always a skill. Mostly everything is a skill that can be improved, and especially communication, absolutely. Just putting that out there. But anyway, there was great evolutionary pressure to develop speech, right, and be a good communicator, right? However, on the contrary, there was not really, I don't think there was much evolutionary pressure to think or to be able to do highly abstract, complicated mathematics. I mean, certainly, like counting things, maybe simple arithmetic, like sure, okay, that could be useful, potentially. But let me tell you, math, honestly, when people say math is hard, they are not wrong in the sense that math can get very difficult. Like even me, who's studied mathematics for 3 years at university, plus I was very interested in the subject at high school and middle school. There's still so much that I don't know, so much that I don't understand, so much that I struggle with. So believe me when I say math, in a sense, it's difficult, right? Our human brains are not naturally very good at doing math, right? Okay, but then there are these mathematicians, right, who do math anyway, and they enjoy it, and in some sense, I would say they're having great success with it. So what's their secret? Why do some people do okay at math, right? And that is what motivates me to claim that mathematics is the art of training your brain to associate abstract nonsense with concrete ideas. I think that's kind of important. So let me actually try to write that down. So let me try to get maybe more space here. So mathematics is all about training your brain to associate abstract nonsense, abstract nonsense. And when I say nonsense, well, maybe I'll give you I'll give you an example in just a second. Abstract nonsense with concrete ideas. Concrete ideas. I'm very afraid of whether this is going to show up on camera. I don't have a lot of experience with this, but let's see. Hopefully it works out. Concrete ideas. Right. Now, let me show you an example of abstract nonsense. It's certainly not the worst example of abstract nonsense that I could come up with, but it's an example nonetheless. So, in general, it holds... Hold on, let me actually think about this. So, A implies B is equivalent with saying the negation of B implies the negation of A. For some of you watching, you've already had maybe training in mathematics, so you recognize what this is. You're like, well, why are you putting something that's totally obvious on the board? But for the rest of you, you're probably already almost clicking off the video because you're like, oh my goodness, what is that? I'm scared. I don't want to deal with this. But listen, this is one example of what I would call abstract nonsense. It's characters that I've written here, and to someone who's untrained, it doesn't automatically translate to anything concrete or anything that could be understood. And honestly, I will be completely honest, like, it does not translate to anything super concrete in my brain either, right? Because sometimes maybe you're used to, like in elementary school, you know, if you had, let's say, a fraction like 3/5, then you would draw a pie, divide it up into 5 pieces, which is very difficult for me to do. 1, 2, 3, 4, 5. So that's around 5 pieces, and you would color in 3 of them, and then this would sort of describe the quantity 3/5, right? We all know that, right? Now, I would say this is pretty concrete, but this right here, this is, I can't claim to be able to produce something this concrete, this level of concreteness. I cannot reproduce for this, because this is abstract nonsense. But listen, what I can do is I can just come up with I will put quotations here. I can come up with a concrete idea. It's kind of a concrete idea that really I just came up with to try to describe this result to myself in a way that I can remember it, right? So at this point, you know, I will say that this result is known as the, was it contrapositive or contraposition? I think it was the contra, because in Finnish, it's contraposition, translated literally, but I think in English it is contrapositive, right? Now, of course, the name of this logical phenomenon, it doesn't matter, right? But I'm just saying that's the name of this result. Now, the way that I remember this result, and you don't have to know what any of this means, right? This is just the introductory video, right? But we can have these implication arrows, right? And we can have these equivalence arrows. And the way that I remember, or a property that I remember about implication arrows is that anytime you have an implication arrow where A implies B, then I remember then this is the same thing as saying that B anti-implies A, right? Now, what does anti-imply mean? It doesn't mean anything. It's not standard mathematical jargon. People don't say that. frankly, it's just something I made up. I made it the frick up. But it helps me remember the result. So A implies B. Well, I remember that that's the same thing as B, anti-implying A. Now, maybe we could have some sort of notation for that. So B anti implies A. And these two are kind of the same thing. And what this anti implies means is that the negation of this implies the negation of this. So I've redefined, or I've defined my own logical operation called this anti-implication, which means that not B implies not A, to help me remember that anytime I have an implication where A implies B, I also have an anti-implication in the other direction where B anti-implies A, right? Now, is that super helpful for remembering this result? Is that what I would teach everyone, regardless of anything? I don't know. Not necessarily, right? Like, what I'm not saying, I'm not saying that this is how you should think about the contrapositive result. Rather, what I'm saying is that you need to take in this abstract nonsense, then think about it, let it chill in your own brain, and then think of ways that help you understand it, right? And I'm sorry about this example because for a lot of you watching, this was an example where I turned abstract nonsense into more abstract nonsense, right? It probably didn't really explain anything. But, at a certain point, you're able to construct all these different ideas in your brain, and you've maybe verified ones that they do make sense, and then you construct these ideas in your brain, and the ideas just make sense to you. They've become concrete ideas to you because you've spent so long thinking about them, right? And again, what I'm saying is this doesn't immediately make sense, but you can think about it in your own words and make it make sense to your brain by turning abstract nonsense into something concrete that you can work with. So this is an abstract statement, while this is an observation where A implying B is always the same thing as B anti-implying A, right? And then you can think, well, why does this hold? And you can start to, think about examples and try to further make it more concrete in your brain. I'm not going to try to do that here because honestly, logic can be very difficult to explain. So maybe this wasn't the best example in that regard. But the idea behind math is being able to read difficult-looking notation, difficult-looking symbols, and turn that into something that you can understand. And that's not always easy to do. It can take very long, right? But it's very rewarding once you build up your own understanding. Trust me, it feels very good when you feel that you have a nice way of thinking about something, or you think you understand something. And math it's not about the symbols, it's about the ideas. And to illustrate that further, I'm gonna give a little thought experiment. So let's think about the way that we humans learn language. So I actually have an anecdote with my niece, but we'll get to that later. So let's imagine that there's a child who's been raised in a box. Okay, this is sounding very bad. But basically, let's say the child gets a lot of toys. I don't know how to draw toys, but the child gets toys, gets food. The child is happy, but the child is raised sort of isolated from the outside world. So the outside world is here, outside, and the child is isolated from the world. And in particular, the child is not taught language. So the child can't speak. The child can't speak at all, right? Now, this is definitely starting to sound like child cruelty. I'm sorry, but this is, of course, luckily, just a thought experiment. So if we have a child who hasn't been taught to speak, then now if you were tasked with trying to teach the human how to speak, then how would you do that? Because when you come across someone, let's say there's someone on the outside who knows how to speak, right? I don't know if you can see this, but this person knows how to speak, okay? And if there's a word that they don't recognize, then we can give them a dictionary, and in the dictionary, we can define the word to this person using words that they're already familiar with, right? So we can use pre-existing words to define new words. That's not revolutionary. But why? What do we do if this person has never learned a single word, right? What do we do in that case? Well, if you started trying to explain, okay, so you know how there's the outside, right? And there's different colors, right? There's green. Green is like grass. You try to explain these things, but the person who can't speak probably isn't even paying attention to you because they cannot understand a single word of what you're saying. Now, unfortunately, mathematics often tends to be like that, where you try to explain math to someone, and they've never seen the math. They've never gone out there and experienced the math for themselves. So they just have nothing to latch onto. And if you try to explain something in terms of math or even in terms of something else, it's not going to register. It's not going to register at all. So how do babies, for example, how do young children, how do they learn language initially, right? And here's the anecdote with my niece. So when I was hanging out with my niece, who's this is embarrassing. I don't know how old she is exactly, but she's a few years old. She's learning to speak. She can speak a few words maybe. And when I went out with my niece, she would point at objects, and she would say this. She would point at it, and say this, right? And then I would say the name of that object in Finnish because it's our native language, and she would be very happy. She would be and she would repeat the word. So maybe I would say, that's a bush in Finnish. And she would be, bush, yeah. She would be very happy, right? And the way that she learned or the way that she started learning those words is by going out there, going outside and physically seeing the objects and associating the word, the sound bush with the physical object of a bush, right? Now, how does this relate to mathematics, right? This relates to mathematics because the way you learn math is by connecting mathematical utterances to real world ideas. So let me try to give you an elementary example, right? So for example, if we have an equation, then, and this might be familiar to you maybe from middle school or something like that, we can think of an equation as a scale where, on one side we have maybe two boxes labeled X, right? And then on the other side we have a box labeled 6, right? And maybe these signify the weights of the boxes. So now we can write this, if the scale is balanced, then the weight of this object is equal to the weight of this object. So we can form the equation x plus x equals 6 to describe this situation. Now, if you haven't worked with equations before, then this x plus x equals 6 is not going to make any sense to you, right? You're probably not even going to pay any attention because it's just random symbols. But if you can associate these symbols to a scale, because everyone's probably seen a physical scale in their lives, and they can picture like two boxes with an unknown weight to them, and then on the other side a box with weight 6, then now they have a concrete way to think about what this equation could mean. And now we can also maybe think about how one might solve such an equation, right? Because if we have two unknown boxes here, then if we half the weight of this side, right? So we get rid of that, and here we have the weight of this side. Then here on this side we just get 1x, right? And on this side we took out half of the weight, so we're left with 6, right? And of course, if you take out half of the weight here and half of the weight here, the scale is still going to be in balance because it was in balance to begin with. That's, very intuitive. And now we find that the result is that this unknown variable x was equal to 3. And we also noticed that, we could notice that this x plus x is actually equal, it's the same thing as 2 times x, right? And this, connecting these real world ideas to these mathematical symbols is absolutely crucial, right? I mean, this was a very elementary example, one that some of you have probably seen before, right? A lot of you probably already knew how to solve an equation like this. But the same idea holds true in higher level mathematics, just the same, right? You need to be able to come up with concrete ideas, right, that you can work with, right? So you have to connect the abstract nonsense into something concrete. Now listen, as you get better at math, what counts as concrete starts to become more abstract. So you noticed that here, sorry, I just jumped accidentally. So when I turned this abstract nonsense into something that was concrete to me, this anti-implication thing, it might not be concrete to you at all, right? Because what's concrete depends on what you already know, what is already concrete to you. I mean, similarly, like if you had never seen a scale like this in your life, right, then this would not be concrete at all, right? Because you need to have learned how a scale works before this connection makes the situation any easier to understand, right? And we are not born with an innate ability to manipulate logical symbols, right? But in fact, I would claim that we are extraordinarily bad at doing that by default. But we are very good at empirically learning about our world. So if you play around with a scale for a bit, then you'll intuitively, ultimately understand how the scale works. And after you understand how that works, you can start to connect it to math, maybe, right? And of course, since these concrete ideas ultimately can and do end up becoming more abstract as you get better at math, that means that, to give you like a more advanced example, when dealing with linear algebra, and if you've never heard of it, don't worry about it, but we end up having these sequences of vectors, and sometimes a sequence of vectors, so first vector, second vector, third vector. Now sometimes these sequences of vectors can actually be what's called linearly independent or linearly dependent. And it turns out that it is helpful sometimes to think about, to like expand a sequence of vectors one by one, right? And then write down whether the subsequence up to that point is linearly independent or dependent, right? So it might be that the first vector alone, well, that's probably linearly independent. And then as you take the first and the second vector, that might be linearly independent too, these two together. But then after the third one, it might be that they're no longer linearly independent. And after that, we take the whole sequence, well, it's still linearly independent, right? And at this point, right, it actually does not matter how many more vectors you add to this sequence. It's always going to be not linearly independent anymore, or it's going to be linearly dependent. Now, if these are probably just words that don't make any sense to you, but basically, this is an abstract diagram, right? This is not a scale in the real world, just like the anti-implication was not a scale in the real world. But on the other hand, it's also not formal mathematical nonsense in the sense that, this is just check marks and X's, right? Those are symbols that you've probably used in your life before. And then I just put a check mark or an X under each vector, and I understand that the implication or the idea is to consider increasing sequences of vectors like this. And for each sequence, I look at whether it's linearly independent or not, right? And this way of looking at the situation, like, it's kind of abstract. I mean, you don't see check marks and X's in the real world outside of, maybe if you take notes or something. But it's also not, it's not like, this isn't a mathematical statement. What I drew here is just a random illustration, right? So this is a concrete idea. It's a concrete idea that helps you understand the situation, even though it's still kind of abstract, right? And I think mathematics, at its core, it's this beautiful dance between stuff that is very concrete. Yes, that makes so much sense. It's trivial. Trivial is a word that mathematicians like to use quite often, right? And then sometimes stuff is very abstract. It's just symbols, but what do the symbols mean? I don't know. I wish to understand it, but I don't. But I will just keep on with the algebra. I will do the algebra, and maybe ultimately the symbols will reveal something to me. It's this dance. And if you get caught up in the abstract symbol manipulation, then, listen, sometimes just solving an equation, it's just symbol manipulation, and that's the end of that. But sometimes, to really understand how to formulate a proof, you also need to form very informal, concrete ideas in your brain that are not mathematical, that are just scribbles, essentially. Or you might have to come up with ridiculous ideas that no other mathematician uses, like anti-implication. I mean, what's that? That's crazy. No one ever uses anti-implication. Just use implications and negations like a normal person, right? But sometimes this nonsense that you come up with helps you tremendously because it builds up this mathematical vision inside your head. And well, I'm gonna be honest, it's not always easy. It's certainly not easy, especially when you're just starting out. It's not easy to come up with the right ideas and the right visualizations. It's absolutely very difficult. And rest assured, it actually has sometimes a very seemingly simple proof for me to really internalize it and understand it. It could easily take me 20 hours or something to understand something, right? As an example, this vector stuff, it's related to a result that basically finitely generated vector spaces, if they have a basis, then all such sequences, all such bases have equal cardinality. That's a very well-known result, and it took me, last summer, maybe, I would say maybe 20 hours, maybe a bit more, to really understand all the details of the argument, right? So it took me a very long time. And listen, another thing is that I didn't understand it. I didn't do a 20-hour marathon, and at the end, I was like, oh, yes, now it finally makes sense. No. For example, if you're a programmer, then you might be used to the idea that, I'll just sit down for 10 hours, I'll write a lot of code, I'll get a lot of code written down, and then, you sit down for 10 hours, and then you actually do get a lot of code written down, and, you have this really productive 10-hour session, and then the next day, maybe you take the day off because, you just worked for 10 hours yesterday, right? That's very typical for programmers, but it's honestly not so typical for mathematicians. If you can think about a problem for maybe an hour or two, but after that, if you're stuck, listen, take a break, and especially sleep. I cannot emphasize the importance of this enough. Every time I go to bed and wake up in the morning, I have such great, inspiring, amazing ideas in the morning if on the previous day I've been thinking about a problem, right? Then after I sleep, then in the morning, I always have new ideas, or at the very least, the thinking that I've already been doing, it's so much more clear. I can go through the steps in my head so much faster, right? So in programming, what it might look like, or, for some of you, if you're maybe students, then your studying might look like something like this, where, you have 10 hours of work, right? And then you have two days off, so you don't do anything here. And this is maybe Monday or Tuesday, Wednesday, right? And then again, maybe you have this 10-hour super productive session again. But that's not how math works. How I would encourage you to do math is by doing maybe 2 hours on Monday, then 2 hours on Tuesday, 2 hours on Wednesday, right? Do it every day, but don't do it for ridiculously long study sessions. That's not really going to help you. Do it for short periods of time, but be consistent. Be consistent about it. And why is that? It's because when you sleep, you reach understanding, right? Sleep and understanding. These are very linked. These are very linked things. So please, sleep enough. If you've had a day where you've thought very hard about math, then it might be that you actually need to sleep more. That's what I notice. If I'm taking a break from math, which doesn't happen very often, but sometimes one needs breaks, then I notice that I get by with so much less sleep for some reason. But when I do math every day, that's when I sleep for 10 hours every night. So listen, sleep, it's so important. So sleep and understanding are very related concepts. And don't be afraid to fail, because you can keep failing for 7 days straight in math on a particular thing. But then on the 8th day that you actually understand it, and trust me, you will understand it. If you actually keep persistently doing something for 7 days in a row, maybe an hour every day, then eventually, you will make progress. And when you do, it's going to feel really rewarding. But you have to be persistent, and you can't give up, right? And if you're a procrastinator that likes to do everything like a day before the exam, then try to get out of that habit. It's not a good habit. It's not good for you. But yeah, that's about all I have to say about mathematics, right? So especially if you've had negative experiences with math in the past, then I recommend that you go easy on yourself, and you don't pressure yourself to understand something. Because listen, sometimes I feel like the stupidest person on earth when I don't understand something. But that's like a part of the fun. Not understanding something immediately is a part of the fun. It wouldn't be fun if you always understood everything immediately, right? Then it would just be boring, wouldn't it? So yes, and at the core of mathematics is turning abstract nonsense into concrete ideas in your brain. Now, each of our brains work differently, and we have different experiences, and different things are concrete to us. Some things make a lot of sense, other things don't make any sense at all. But all of us, what we have in common is that math does not make any sense to any of us by default, right? So quit thinking that there's some people who read mathematical equations and mathematical statements like it's a novel. No. Because in the ones that do that, they do that after they've trained their brain to associate to associate certain, mathematical ideas with certain diagrams, certain ideas, certain visual imagery, right? Something that is concrete and makes sense to them. And that doesn't happen automatically. But I'll try to help you guys to build up some understanding. And I hope it works. I don't know. But this was the introductory video to the series. Maybe I went on for too long, but I'm very passionate about the subject, so hopefully you find it interesting. Math is a very broad subject. There's a lot to it. And different people have different goals. The goal of this series is gonna be to try to understand things at a pretty deep level, but you don't actually need to understand math at a deep level to be able to apply it in, economics, for example. So if these things also don't make sense, then that's maybe okay, right? And maybe I'll make different kinds of videos in the future. Maybe some videos where we focus more on the mechanical aspects of math, like how you can actually apply math. I mean, I don't know. I don't know what I'm going to be doing with this channel. But anyway, I hope you found this interesting. I hope you're looking forward to the series. And I guess that's about it. So I'll see you in the next one.